Welcome to the Wave, Sound, and Light Notes version 3. The first thing I'd like to talk about is sound. So when we introduced waves, we said there were waves were either mechanical or electromagnetic. And you need to know that sound waves are mechanical. You also need to know what it means to be mechanical. They are mechanical because they need a medium to travel through. That could be water, that could be a slinky, that could be air, but they need a medium to travel through. So sound waves, as mentioned before, do not travel through a vacuum. They do not travel through space. You also need to know whether sound waves are transverse or longitudinal. And sound waves are longitudinal, which means that the way in which they vibrate is which is parallel to the way that the energy is transferred. So if the energy is transferring from left to right, the waves are vibrating from left to right as well. So for sound, the specific pitch corresponds with frequency. So it is the same as frequency. That's a vocabulary word that's specific to sound. The audible range for humans is generally 20 to 20,000 hertz. Of course, this changes with age and with individuals, but sounds that are vibrating at less than 20 hertz or greater than 20,000 hertz are still indeed sound. They're just not audible to humans. Now, that sound is still applicable. There's many applications for those sounds. There's medical applications, there's ultrasounds, there's animal communications, there's sonar communication means that those sounds do exist. This, again, is an example of a longitudinal wave. So a tuning fork vibrates back and forth, and the sound wave will travel away from the tuning fork in a horizontal manner. But you get areas of compression where the areas is in a high pressure area and areas of rarefaction again. So if I was graphing the density of the sound, I'd get high density, low density, high density, low density, or compression, rarefaction, compression, rarefaction. Speed of sound is still, just as because it's a wave, still distance over time or frequency by the wavelength, but it also depends on the medium that you're traveling through. So you do not get a table like this on your reference table. This is from another textbook, but notice here as the temperature of air increases, the speed goes up. So this is the speed that you get on your reference table, 331, but 343 is also a speed that's typically used. Notice here as we go to solids, we get to much higher speeds, so speeds of 5,000 as compared to 300, and sound just transfers much more efficiently through solids. So in general, we get higher temperatures result in higher speeds, and denser media result in higher speeds. Moving forward, harmonics. We talked a little bit before about the fundamental frequency, or the most basic way that something vibrates. It is the lowest frequency in a standing wave. So there is also a harmonic series, and this is not that important for the regions, but it's a pretty cool supplement for honors physics. We get a harmonic series that is integral multiples of this fundamental frequency. These are also called overtones. So it differs from strings to instruments with open ends or one open end. So on a string, we talked about this before, the fundamental frequency, or the most basic wave pattern, is half of a wave. So if I told you the string was 1 meter long, then in order to get a full wavelength, I'm going out to 2 meters. So if this is 1 meter long, the wavelength is also 1 meter, and this is the second overtone, or the second most basic pattern that can be shown. So again, if this is 1 meter, I get a full wave here. So here, this is 1.5 waves. So if this was a 1 meter long string, I could say the wavelength is the number of meters, 1 divided by the number of waves, which is 1.5. Here, I get half of a meter would be the wavelength here. So again, I can figure out the integral multiples of that fundamental frequency, or the overtones. Again, this happens differently with ends of instruments that are open at both ends versus one end. Different instruments function in different ways. We talked about the reflection of a pulse being different on a fixed end versus an unfixed end. So if I have a fixed end or a closed end, the air doesn't have room to vibrate. So basically, if it doesn't have room to vibrate, it's a node or an area of no displacement. Whereas my open end is an area where I can go from maximum positive to maximum negative amplitude, or an antinode. So if I go from node to antinode, I have actually 1/4 of the wavelength. So in order to get, if this was 1 meter long and I had 1/4 of a wave, the full wave would be 4 meters long. I'd have to go all the way out into here to get the full wave. On the second harmonic, I get 3/4 of a wave. Now, that differs if the instrument or the thing producing sound has open ends at both ends. So here I have an antinode, here I have an antinode. With two antinodes, I actually get half of a wave that forms in this kind of tube. And then on the second harmonic, I get a full wave that forms from antinode all the way through to antinode. Beats is a pretty cool thing. So beats is an interference pattern that occurs between two different waves. So if I look down below, I've got a 60 hertz and a 55 hertz. So here they're totally in phase. So again, when we go back to constructive interference, I have a wave up, I have a wave up. The resultant wave is a higher wave or a wave with a higher amplitude. Eventually, because these are different frequencies, they have some, they fall out of phase. So here they're 180 degrees out of phase. So when they're out of phase, I get destructive interference or no displacement. So again, I get a period of high displacement, no displacement, high displacement, no displacement. High displacement for sound is a loud sound. So I go from loud sound to low sound to loud sound to low sound. So the again, this is examples of constructive where I get high amplitude to destructive where I get no amplitude. The beat frequency, and this equation is not on your reference table, is simply the difference in the two frequencies. So you can say F1 minus F2 or F2 minus F1. So this is a pretty cool application that allows you to hear the beats. On this application, I've got a 440 hertz frequency. I'll hit play. And if I have two 440s, they don't have a difference in the sound. But if I change this to 441 and I hit play, I get a beat frequency of 1 beat. If I change this to 2 and hit play, I get a 2 hertz beat frequency. And if I pop this down to 439, I'd still get my 1. So it doesn't matter if it's 441 and 440 or if it's 440 and 439. So, I can just get different frequencies here, and if, this will be a faster beat. And again, this is all a product of constructive and destructive interference. It might be a little bit easier to see on 441. But I have two beat frequencies, a blue and a purple. When they're in phase, I get a high beat. When they are out of phase, I get destructive interference. So again, these are beat frequencies. So sound waves don't really travel out in one dimension like we sometimes model it. They don't even really travel out in 2 dimensions. They travel out in a spherical pattern. So we get, these are concentric waves that travel out, and we get a high area of high compression and area of rarefaction. Again, compression, rarefaction, compression, rarefaction. This has a simulation of a source producing sound. So when it's stationary, the wave fronts are equally spaced apart, or the wavelengths are equal. But as it starts to move, I get different changes in the wavelength. So in front of it, the waves bunch up, and in back, the waves get a little bit longer. This is actually called the Doppler effect. So this is a frequency shift that occurs for both sound and light. I'm not going to make you accountable for the equation for this, but the equations for sound are as follows. The perceived frequency equals the emitted frequency divided by 1 minus the quotient of the source of the sound divided by the speed of the sound in that medium, which is usually about 330. Again, not important for this class for this year, given our situation, but you will need to know the theoretical components of the Doppler effect. So my guess is most people have heard the Doppler effect before. Fire engines, ambulances, NASCAR. So there's a bunch of different examples of that. So here's one example of it. So you can see as the horn comes towards you, you get to experience a little higher frequency than what's emitted. Then as it goes away, you have a lower frequency than what's emitted. This is a pretty good animation of this. So if I just start to play this, well, it's not moving. You can notice that, again, the waves are equally spaced. You know, if I'm at this arrow over here, I get the same frequency of waves as if I'm over here, or if I'm over here, if I'm over here. But as I start to increase the speed, please note now that the waves are bunched up in front of the source. Or I get the waves more frequently, or I get the waves with a shorter wavelength. The wavelength, again, is the distance between the waves. Back here, if I'm behind the object, I get a longer wavelength, and I get those waves less frequently, which is why when the horn travels away from you, it changes from a high-frequency sound to a low-frequency sound. Now, the next piece of this is when the sound starts to approach the speed of sound, when the source is moving at the speed of sound. So if I jack this up here, this means that my source is now traveling at the same speed as the speed of sound. So what happens here is every time I let out a sound wave, I travel with that sound wave. So I get an area of compression, and then I let out another area of compression and compression and compression. Well, when you're talking about sound waves, that compression corresponds with sound intensity. So basically I get a lot of compression all bunched up. It's constructive interference, and I get a really loud sound, otherwise known as a sonic boom. So when I cross the sound barrier, that's what's happening to the wave fronts. They all bunch up. I get a high intensity wave, which is called a sonic boom. Notice here as I speed up above the speed of sound, I still get this constructive interference, but the constructive interference is kind of in a conical pattern. It's a cone around the source of sound. I get this pattern that comes out here. So I still get constructive interference here, but it's not. It's a slightly different pattern than if I have constructive interference from the moving directly at the speed of sound. There's a video compilation of a bunch of planes that are crossing the sound barrier, but this is one such example. Notice here, this is a plane that starts to cross the sound barrier, and when it does, I get so much compression that the water vapor actually turns into water. The water vapor that's in the air turns into vapor. And please note that when I do this, I get that same conical shape around my plane. So pretty cool phenomenon. So again, example of constructive interference when you hear the sonic boom. Again, Doppler effect, just a picture. Observer A gets high frequency. Observer A gets low wavelength. Observer B gets high wavelength, the length between the waves, and lower frequency. One last phenomenon of sound, and this is true of light as well. I get intensity of which is basically how much power I get for a certain area. So notice here, if I'm close to the speaker, I hear a loud sound. If I'm farther from the speaker, I get less sound. So that then results because that sound, the power that you produce, has to cover a greater area. Now, this is not a linear relationship because the area this covers is actually the area of the sphere. So this is the equation for the area of a sphere. So there's an exponential decay as this travels out in sound intensity because it covers more area. We don't usually do watts per meter squared for intensity. Most of the time in real life we change this to a decibel rating, which is decibel level. which is a logarithmic rating of sound intensity. So